We continue our lectures on transport phenomena in furnaces, and fluid flow was our topic. We have derived an equation to calculate the velocity of fluid flowing in the duct or flue or wherever in the furnace the fluid is flowing. So, today I will be illustrating the use of the equation that was derived to calculate the velocity through a problem. So, I will tell the problem. So, a pitot tube is installed in a pipe or duct, whichever you want to call, of diameter 0.3 meter, which carries air at 70 degree Celsius. Atmospheric pressure is 745 millimeter of mercury. Pitot tube measures pressure difference that is equal to 50 millimeter water. 50 millimeter of water. Assume pitot tube coefficient, that is Cp, which we have introduced in the formula, is equal to 1. That is, it is a very well designed pitot tube. So, you are required to calculate flow rate of air. Flow rate of air passing through the pipe. Now, the problem can be illustrated as this way. If this is the pipe, air is flowing and the atmospheric pressure is 745 millimeter mercury. So, here there is a pitot tube is placed. This is our pitot tube. Is placed at the center of the pipe, and it is at this position. So, the pressure difference of 50 millimeter of water, which is measured through the pitot tube, it is in fact at this particular point, that is at the center of the airflow. So, if the air is flowing this way, this is the flow of air, then this particular streamline will impact the pitot tube, and hence you read the pressure differential. So, what pressure we are recording is the pressure at the center of the pipe. So, of course, what we will be determining from this pressure measurement will be the maximum velocity, and from there we have to calculate the flow rate of the air. So, this is in fact a problem. Now, something conversion factors are also given, say 1 millimeter of mercury, that is given to be 133.2 Newton per meter square, whereas 1 millimeter water that is given 9.806 Newton per meter square. Now, these conversions you may be needing. Also, it is given viscosity of air at this temperature is given to you 20.6 into 10 to the power minus 6 kilogram meter per second. Now, we have to solve this particular problem, and as we know from the pitot tube, that is V maximum, that is equal to Cp into square root of 2 into delta P upon rho. So, we have to calculate now the V maximum. That is, first we will calculate V maximum, and from V maximum we will calculate the flow rate. So, we have to first of all find out the density. So, density rho, that is equal to P upon RT. P is 745 millimeter. So, you have to convert into Newton per meter square, and the value of rho will be 1.01 kilogram per meter cube. So, this is what the value of rho. Now, we have to convert delta P, which is given in 50 millimeter of water. So, 50 into 9.806 Newton per meter square. So, and well, just multiply it, that will be 490.3 Newton per meter square. Now, we know all the variables in this equation. So, V maximum, that is equal to 2 into 490.3 upon 1.01. So, that will give us 31.2 meter per second. So, this illustrates how the pitot tube can be used to measure the velocity of air or fluid in the pipe or in the duct. So, this is the maximum velocity at which the air is flowing. Now, if we calculate the flow rate, so flow rate simply will be equal to rho u into A. So, if we do all the substitutions, then we will be getting 2.20 meter cube per second. Now, this is based on maximum velocity. And as you recall, there is a velocity distribution in the pipe. So, if you want to calculate the average air flow rate, that means you have to calculate average velocity, and this average velocity may be very close to the flow rate of the air rather than flow rate that we obtained from maximum velocity. So, in that particular case, what we have to do? We have to utilize this expression V average upon V maximum, that is equal to 0.62 plus 0.04 log of d V maximum upon rho into mu. We know all these variables, so we can substitute and find out, and this value will be coming to equal to 0.83, and hence V average, that will equal to 25.9 meter per second. Now, we can determine now the flow rate. Say flow rate, that will come out to be equal to 1.83 meter cube per second, which is based on V average. So, that is the difference between the flow rate when maximum velocity and average velocity are used. So, if I now want to extend this particular problem further, so I say now if the pipe length, let us see, if the pipe length is 200 meter and air is discharged at 1.25 atmosphere pressure, then calculate the power of the fan required to draw air from rest. Atmospheric pressure is same as earlier. Atmospheric pressure is 745 millimeter mercury. That is what is given earlier. Now, since the pipe length is involving and air is entering from rest and it is discharged at 1.25 atmospheric pressure. So, now we have to calculate the power of the fan. If I represent again through a diagram, then it looks something like this. So, this is the pipe whose length is given 200 meter. Air is drawn from the rest, so somewhere here. Air is entering. Somewhere here I require to have a fan, of which I have to calculate the horsepower, and now I am taking the air is discharged, say at 1.25 atmosphere, which is given. So, now if I want to solve this problem, what I have to do? I have to first of all take, this is my section 1 and this is my plane 2. Naturally, I have to do the mechanical energy balance in order to solve this particular problem. So, now what I have done here, I represented plane 1 and plane 2. Plane 1 is slightly upstream the entry of the pipe, plane 2 is slightly downstream at the exit of the pipe, meaning thereby the V1 and V2 will be very, very small and hence they can be neglected. So, now applying mechanical energy balance. So, applying a mechanical energy balance, mechanical energy balance between 1 and 2, then we get G delta Z plus P2 minus P1 upon rho air plus V2 bar square minus V1 bar square upon 2 minus F plus F, that is equal to 0. F is the frictional forces. Now, since it is a horizontal pipe, so for horizontal pipe delta Z is equal to 0. So, our equation becomes now delta P upon rho air, and also V1 is equal to V2 because they are very negligibly small, we can neglect it, and F, you know this equation F, that is equal to 2F L by D V bar square plus half EF1 V bar square plus half EF2 V bar square. So, all that we have to replace. So, that will be equal to plus V bar square 2F L upon D plus half EF1 plus half EF2, where EF1 is losses due to contraction and EF2 losses due to expansion. Now, you have noted that at the inlet of the pipe, as the fluid enters, it contracts. At the exit, the fluid expands. So, accordingly, the values are given, say EF1 that is equal to 0.4 and EF2 that is equal to 1. Now, V bar is the average velocity in the pipe. However, if you wish to calculate by taking maximum, you can do that, but the correct would be to take the average velocity of the pipe, and you know previously we have determined the average velocity was 25.9 meter per second. So, all that I have to substitute these values now into this equation, and this now let me just put it, this equation is a separate one. These are the values. Now, say this equation is plus minus m that is equal to 0. So, what I have to do now? I have to substitute all the values, and if I do that, you can substitute, you can calculate the value of delta P. Delta P will be equal to 0.25. So, if I do that, then m, which is the work done, that will come equal to 22,787 meter square upon second square. All that you have to substitute the values. Delta P is 0.25, convert into Newton per meter square. Rho air we have already determined, all these values you have to import over here and you have to substitute, and this is the work done. Now, if you multiply by the amount of air, then you get the horsepower. So, the power of fan that is required, that is equal to 54 kilowatt or 71 horsepower. So, that will be the answer. So, in fact, what I have illustrated is follows, that how to use the pitot tube measurement to come to the power of the fan if the need arises to do that. Otherwise, in many cases, the velocity of the fluid is important, and pitot tube can be very easily used to measure the pressure and hence to calculate the velocity. It is also very easy to manufacture the pitot tube. Now, I will give you a problem that you should solve yourself. So, let us put self assessment problem that you should solve yourself. What I am writing now, in a duct of diameter 0.5 meter, pitot tube is installed as shown in the figure. As shown in the figure which I am going to draw. The air at rest is drawn by a fan. The air is at 298 Kelvin and 1 atmospheric pressure. The air discharges at 1.15 atmospheric pressure. If the pitot tube measures a pressure difference, say 30 millimeter water, calculate A, velocity of air, P, average velocity of air, C, power of the fan. Now, I will draw a figure so that you understand. So, this is the duct or pipe. Here I have installed a pitot tube. Air is flowing. This is exiting. Somewhere here I have put the fan, of which I have to calculate what is the power required, and the duct length, which I forgotten, I can give you here. The length of the duct is 160 meter. Length of the duct is 160 meter. So, here some values you may be requiring. Say, take Cp, that is equal to 1. EF1 take 0.4, EF2 take, this is equal to 1, and viscosity of air, that you take 1.85 into 10 to the power 5 kilogram meter per second, and I do not think any other value than you require. So, you can calculate these values and try that you can understand. Now, here it is important again to refer to the plane. So, somewhere you have to put your plane 1 somewhere here and plane 2, this will be plane 1 and this will be your plane 2. So, apply the, first of all calculate the velocity, then apply the mechanical energy balance and so on and so forth. So, here V maximum, that will be equal to 20.8 meter per second. V average, that will be equal to 17.8 meter per second. And if you apply mechanical energy balance, then the work done by the fan, though it is not asked, but you can also calculate by fan, that will come out to be equal to 11,925 meter square second square, and power, that should come equal to 56.82 kilowatt based on V average. So, that is how you will be solving this particular problem. So, with this, the illustration of velocity meter is complete, and now the next part of the fluid flow measurement is that of the head meters. Now, let us see head meters. What does it mean, head meter? A head meter is used to measure the pressure differential. It can be installed in a pipe or in a duct or in a flue, and one can measure the pressure differential, and one can correlate this pressure differential with that of the flow rate. So, there are different types of flow head meters are used. Say one head meter is called orifice. An orifice, in an orifice it is a thin plate, with a hole in it, and it is placed across the flow. Another head meter is called Venturi, meter. Now, Venturi meter has to be designed. In the Venturi meter, the flow area decreases in the direction of the flow, attains a minimum value which is called the throat of the Venturi, and then again increases in the direction of the flow. So, in a way, a Venturi is frictionless, ideally speaking. Third type of head meter, they are the nozzles. Nozzles, they are characterized in that the cross sectional area decreases in the direction of flow and attains the minimum value at the exit, which is called the throat of the nozzle. So, it is also has a friction, but somewhere in between Venturi meter and orifice. So, an orifice, it looks, for example, say this is the pipe. I just take a plate, and if this is the center line, then an orifice, say the plate over here of some hole. So, this is the orifice. So, this is the orifice, and if you want to represent the flow lines, that is how the air will flow, and somewhere this is the flow direction of air. So, air will go this way, and how the air flow. So, at this here, lot of eddies are generated. Here, the eddies are generated, and because of these eddies, there is a loss of pressure. So, this is typically the flow of, say, air through a orifice looks, and other flow lines can also be shown. This one, that is how the orifice. Now, if I draw a Venturi, say let me draw a center line. So, the flow cross section area for the flow, it decreases, attains a minimum value, and then it further increases in the direction of the flow. So, here the flow line, suppose the air is flowing this way, then it will go flow this way, this way, this way, This is the flow of air. Flow of air. So, this is the venturi, and this was the orifice. So, here the chances of eddies formation is very minimum, and hence very low loss of pressure to the tune that it is almost a frictionless. Whereas a nozzle, in a nozzle, if this is the central line, this is a nozzle, and this portion is called throat. So, here the flow lines will go, there is the flow discharges here, a lot of eddies would be created, and there will be a loss of pressure in between the two. So, now let us see how we can measure the pressure differential. So, I take first of all, whether I take orifice or I take venturi or I take nozzle, the pressure measuring device will be same. The only difference will be that of the discharge coefficient. So, let us take the first of all, for example, the orifice. So, I represented orifice, this is central line, and this is the pipe. Here I am putting an orifice, that is a simple cross section area. So, the air flow will go this way, let me represent, this is section 1 and this one is section 2. This is at the entry D1 is the diameter of pipe, and D0, that is from here, that is this one to this one, D0 is the diameter of the orifice. D0 is the diameter of orifice. Now, we have to find out and correlate pressure difference with the velocity and also with the flow rate of the air. So, what we have done, we have selected section 1 and section 2. Now, what we do, we attach a pressure differential, that is a manometer, somewhere here and between this section. This is the manometer. And we will be reading this, say, this is the pressure difference that we are reading. Delta P. Now, note, in order to measure the maximum pressure difference, we have to locate section 2 such that the measurement give you maximum pressure. Logistically, when we have diameter of the pipe D1 and diameter of the orifice as D0, then naturally D0 is less than D1. So, logistically, our second leg of the manometer should be at D0. But when a fluid flows through an orifice, the flow line contracts, and on account of contraction of the flow line, a minimum cross sectional area for the flow results downstream the orifice. With that I mean that though the minimum cross sectional area should have been at the point D0, that is the diameter of the orifice, but because of the fluid flow or because of the dynamics of the flow, the minimum cross sectional area point, it shifts downstream the orifice, and this one, which is the somewhat less diameter, which I will call as D2. So, that means this diameter is D2, this diameter is D0. So, D2 is diameter at which minimum cross sectional area results, at which minimum cross sectional area is there. And as such, this D2 is called the formation of vena contracta. Formation of vena contracta, and as such, the vena contracta is the formation of minimum cross section in the flow downstream the orifice. So, this is a typical for the orifice, because when you locate the second leg of the manometer, if you locate at the orifice, then you will not be reading the maximum pressure, you will be reading maximum pressure downstream the orifice. So, that is what the most important point in case of orifice, the formation of vena contracta, that is the minimum cross section somewhere downstream the orifice. It is at that vena contracta we have to put the second leg to measure the maximum pressure differential. Mind you, this is a dynamic thing. It is very difficult to locate the the vena contracta when the fluid flows from inlet to exit. All that we know is static diameter at the inlet and diameter of the orifice. So, that point is to be kept in mind. Now, say we apply mechanical energy balance, mechanical energy balance at 1 and 2, it is horizontal, delta z equal to 0. For the time being, what we are considering, say let me put delta z is equal to 0, there is no fan, so m is also equal to 0, and for the time being we are assuming that frictional forces, that is the F, that is also equal to 0, though we know that there is a friction and there is a loss of pressure that will take into account in by some other way. So, if we apply this balance, then we get P2 minus P1 upon rho plus V2 bar square by 2 minus V1 bar square 2, that is equal to 0. Now, remember our 1 and 2, 1 at the inlet and 2 is at the vena contracta, not at the orifice diameter. Note this particular point is important. Now, say from continuity equation, we know that rho 1 V1 A1, that is equal to rho 2 V2 and A2. Since fluid is incompressible, so rho 1 is equal to rho 2. So, we get very simple relationship V1 bar, or let me put average velocity. So, V1 bar, that will be equal to D2 upon D1 square into V2 bar. Now, we insert this expression into our mechanical energy balance and simplify it, then we get say P2 minus P1 upon rho plus V2 bar square by 2 minus d2 upon d1 to the power 4 into V2 bar square upon 2, and that should be equal to 0. If I simplify this, then I will be getting V2 bar square by 2 1 minus d2 upon d1 raised to the power 4, that is equal to P1 minus P2 upon rho. So, I simplify further, I will be getting now V2 bar, that will be equal to 2 into P1 minus P2 upon rho 1 minus d2 upon d1 to the power 4, and that is the closure of this one. Now, remember, I again stress and write with a different ink that d2 is diameter at vena contracta. Vena contracta, and that is a important thing, because then and then you will measure the maximum pressure differential. We note and we know and we have done. What we have done? We have positioned second leg of the manometer at the vena contracta. It is very difficult to determine in practice. So, in fact, we have to use a sort of coefficient of discharge in our calculation, which accounts for the losses and geometrical configuration. In other words, the shifting of the minimum cross sectional area downstream the orifice will lead to the maximum pressure. But then we know only diameter d1 and d0. We do not know d2. d2 is a dynamic. If suppose flow rate is very high, flow rate is very low, then the vena contracta will shift and you will not be able to locate and you will not be able to do anything. So, in order to locate, or in order to now use this expression for V2 bar in terms of known parameter, what we will do? We will relate it to the so called diameter at the inlet and diameter of the orifice. So, we relate the so called orifice velocity. Now, we relate say orifice velocity V0 bar, that is equal to, say we write now V0 bar, that is equal to CD 2 upon rho P1 minus P2 upon 1 minus b to the power 4, that is equal to the power 1 by half, where b that is equal to d0 upon d1. CD is the coefficient of discharge. Coefficient of discharge. Now, this equation is close to the known values of orifice. We know d0, we know d1. All that we unknown is the coefficient of discharge, and this coefficient of discharge has to be, known or has to be determined. So, we can further simplify, say V0 bar, we write K 2 by rho P1 minus P2 power 1 by half. Now K is flow coefficient. K is flow coefficient, and that is equal to CD upon the square root of 1 minus p to the power 4. So that is how this now the equation. Now if you want to, now we have a incompressible fluid and compressible fluid. Incompressible and compressible. Say for incompressible, density is constant. So we can determine now the mass flow rate of fluid. Mass flow rate, say m, rho, velocity v0 bar into a. So we can substitute all these values and we can get K into A0. A0 is the corresponding to the area at the orifice, square root of 2 rho P1 minus P2. That is for incompressible fluid. For incompressible fluid. Now for gases, this mass flow rate of air m, that will be equal to K y A0 2 rho P1 minus P2, where y is an additional factor that is called expansion factor. That is called expansion factor. Now this y, it can be determined say it can be determined by y is equal to 1 minus P2 minus P1 upon kappa 0.41 plus 0.35 b to the power 4, and this expression holds for, I will write down a different orifice and square edged. Orifice which is of square. This, from this equation you can calculate y. Now the other head meters which are Venturi and nozzle, similar expression is valid, that is m is equal to K y A0 square root of 2 rho P1 minus P2. Close here. So what this expression is at, say for Venturi and nozzle, the expression m is equal to K y A0 2 rho P1 minus P2 is valid. The same, only here the A0, that will be equal to cross section area. A0 correspond to cross sectional area of throat. That is, this is the minimum cross section area, because in case of Venturi and nozzle, a formation of vena contracta is not there. So the minimum cross section which is at the throat, it can be used to determine the value of A0. Now, the difference would be here. You have to find out now how to determine y. For all compressible fluid, you have to find out the value of y, and the value of y, it can be determined by, this is the for Venturi. Now, we have to determine the value of y. So, expansion factor for y, expansion factor y for Venturi and nozzle, it can be determined by the following expression, that is y is equal to kappa 1 minus P2 upon P1 raised to the power kappa minus 1 upon kappa, bracket closed, 1 minus B to the power 4 divided by kappa minus 1 minus P2 upon P1 P2 upon P1 raised to the power minus 2 upon kappa minus B to the power 4 and whole raised to the power 1 by 2. Now, here kappa is an isentropic exponent. Tropic exponent, and this is equal to 1.4 for all diatomic gases. Diatomic gases, and kappa is 1.667 for monoatomic gases like say argon, helium, here say like O2, N2, air, this is what. So, you can determine y, and rest B already we have determined. Now, B in case of Venturi and nozzle, that will be equal to D2 upon D1, where D2 is the diameter at the throat, D1 is the diameter of the pipe. P2 and P1, they are the pressures at the respective locations. Now, we also note that the orifice plates, they also cause a loss in pressure. That means, use of orifice will also lead to a permanent losses or permanent loss of pressure. With that, if suppose if the fluid is flowing in a direction, in case of frictionless, there will be no loss. So, the permanent pressure loss, in case of orifice, it can be calculated by say delta P loss, that will be equal to 1 minus B square into P1 minus P2. Whereas, for Venturi, they are almost frictionless. So, their permanent pressure drop that is equal to 10% of the measured differential pressure. Now, with this we have derived to calculate the velocity, and in the next lecture I will illustrate the use of this expression to determine the Venturi and orifice.